Imagine a signal so powerful, it crosses billions of light years in the blink of an eye. A burst of energy so intense, it outshines entire galaxies for just a fraction of a second. This isn't science fiction, this is real. These are fast radio bursts, or FRB, one of the most electrifying mysteries in the cosmos. For decades, astronomers have been scratching their heads over these fleeting, ultra-powerful radio waves that flash across the universe without warning. They arrive from the deepest reaches of space, last mere milliseconds, and then vanish, leaving behind more questions than answers. What could possibly generate such a staggering amount of energy in such a short time? Where are they coming from, and why do some of them repeat while others disappear forever? Fast radio bursts are like cosmic fingerprints. Each one carries secrets about the faraway corners of the universe they've traveled through. Some scientists think they might be the death throes of collapsing stars, while others suspect bizarre, hypermagnetic neutron stars, or even, dare we say it, signs of advanced alien civilizations. The truth is, we still don't know, and that's what makes this story so thrilling. Every new detection shatters old theories and opens up wild new possibilities. It's as if the universe is playing a high-stakes game of hide and seek, teasing us with clues but refusing to reveal the full picture. So buckle up, because today we're diving deep into the enigma of FRBs, unraveling 30 of their biggest mysteries, from their mind-bending origins to the tantalizing hints they might hold about the fabric of space itself. This isn't just a story about strange signals from the void. It's a detective story, a cosmic treasure hunt, and a glimpse into how much we still have to learn about the universe. By the end of this journey, you'll see the night sky a little differently, knowing that out there, hidden in the darkness, are bursts of energy so powerful and so mysterious, they defy everything we think we know. Ready to crack the code? Let's begin. The story of fast radio bursts begins not with a live observation, but with a cosmic cold case, a mysterious signal hiding in plain sight for years. Back in 2007, astronomer Duncan Lorimer and his student David Narkevic were sifting through old data from the Parkes radio telescope in Australia when they stumbled upon something extraordinary. Buried in observations from 1967 was a single, dazzling spike of radio energy so intense it stood out like a flare in the night. Lasting just 5 milliseconds, this burst, later named the Lorimer Burst or FRB 010724, packed as much energy as the sun releases in 30 days. At first, the discovery sent shockwaves through the astronomy community, but not everyone was convinced. The signal seemed too bright, too bizarre to be real. Some researchers wondered if it could have been a glitch, maybe interference from Earth or a malfunction in the telescope. After all, nothing like this had ever been seen before. But when other teams reanalyzed the data, the signal held up. It was real, and it had traveled an astonishing 6 billion light years before reaching us. What made this burst even more puzzling was its ghostly nature. Unlike later repeating FRBs, the Lorimer Burst was a one-time event, here 1 millisecond, gone the next. Its brevity and power defied all known cosmic phenomena. Neutron stars too weak, supernova too slow. The only clue was its dispersion measure, a fingerprint showing how the burst's waves had been slowed by electrons in deep space, proving it came from far beyond our galaxy. This accidental discovery rewrote the astronomy playbook. It was as if scientists had been listening to the universe's whispers for decades, only to suddenly hear a scream from the void. The Lorimer Burst didn't just open a new field of study, it exposed how much we didn't know. If such violent, invisible explosions were happening across the cosmos, how many had we missed? And what could possibly be powerful enough to create them? The hunt for answers was on. Just when scientists thought they had fast radio bursts figured out as random cosmic explosions, the universe threw them a curveball. In 2012, the Arecibo radio telescope in Puerto Rico detected something unprecedented, a burst that didn't just flash and disappear, it came back. And then it kept coming back. This rebel signal, named FRB 121102, wasn't just a one-hit wonder. It was a repeating phenomenon, pulsing over and over like a celestial heartbeat. For the first time, astronomers could study the same FRB multiple times, and what they found was staggering. When they finally pinpointed its origin, the burst was traced to a tiny, chaotic dwarf galaxy 3 billion light-years away, a place where stars are born and die in furious bursts of activity. The location was a goldmine of clues. This wasn't some quiet corner of the universe. It was a cosmic factory of extreme physics, the perfect breeding ground for something as violent and unpredictable as a repeating FRB. Theories exploded. Could these bursts come from Magnetars, neutron stars with magnetic fields so strong they could strip the iron from your blood from halfway across the galaxy? Magnetars are known to produce powerful flares, and their extreme environments match the erratic behavior of FRB 121102. But here's the twist, not all repeating bursts act the same. Some fire off in predictable patterns, while others seem completely random, as if something or someone is flipping a switch. That uncertainty has led to even wilder speculation. Could these repeating signals be artificial? Imagine an alien civilization harnessing the energy of a neutron star to power interstellar beacons, or perhaps unintentionally blasting radio waves across the cosmos as a byproduct of their technology. It's a long shot, but the mere possibility forces us to confront how little we truly understand. The discovery of repeating FRBs didn't just change the game, it broke the rules entirely. No longer could astronomers write off these bursts as isolated cosmic accidents. Now they had to grapple with the reality that some of these signals were deliberate, repeating enigmas, each one a tantalizing piece of a puzzle we're only beginning to assemble. And if some repeat, what does that mean for the ones that don't? Are they fundamentally different, or are we just not listening long enough to catch their encore? The answer, like the bursts themselves, remains maddeningly out of reach for now. Among the strange family of fast radio bursts, one stands out not just for repeating, but for doing so with clockwork precision. FRB 180916.J0158+65. Unlike the erratic bursts of its cosmic cousins, this one follows a bizarre 16.35-day cycle. For about 4 days, it fires off bursts like a cosmic machine gun before falling silent for the next 12. This isn't random chaos, it's a celestial metronome ticking with a rhythm that defies easy explanation. Astronomers were stunned when they first detected this pattern. Nothing in their existing models accounted for such perfect periodicity. If these bursts come from magnetars, why would they take a 2-week break? If they're caused by cataclysmic stellar collisions, how could they repeat so predictably? The leading theory now points to a cosmic dance, a neutron star locked in orbit with a massive companion, perhaps a giant star or even a black hole. As the neutron star wobbles through its orbit, its powerful magnetic field might funnel energy into brief, focused beams that sweep past Earth like a lighthouse, visible only during specific phases of its cycle. But here's where it gets even stranger. Some researchers argue that this 16-day rhythm could come from a wobbling magnetar itself. Imagine a spinning neutron star with a tilted magnetic axis, slowly precessing like a wobbly top. Every time its magnetic poles align just right, it might unleash a burst. Others suggest a more exotic scenario, a neutron star plowing through a dense disk of material around its companion, igniting bursts like clockwork as it periodically interacts with the debris. The implications are profound. If even one FRB follows a strict timetable, it means these phenomena aren't just chaotic explosions, they're governed by unseen celestial mechanics we're only beginning to decipher. It's like discovering that what we thought were random lightning strikes are actually pulses from some vast, hidden engine in the cosmos. And if one behaves this way, how many others might be doing the same, their patterns still hidden in the noise? Every new detection peels back another layer, revealing a universe far more intricate and far more mysterious than we ever imagined. For years, astronomers had chased fast radio bursts across billions of light years until one finally erupted in our cosmic backyard. In April 2020, a deafening blast of radio waves shook the Milky Way, and this time we knew exactly where it came from. The culprit, a restless magnetar named SGR 1935+2154, a city-sized neutron star with a magnetic field a trillion times stronger than Earth. This wasn't just another distant mystery, it was a smoking gun, the first concrete proof that magnetars could produce FRBs. The moment this magnetar flared up, telescopes around the world scrambled to capture the event. What they recorded was astonishing and intense millisecond burst of radio waves, paired with a simultaneous X-ray explosion. That combination was critical. While magnetars were already known to emit X-rays during violent starquakes on their crusts, no one had ever caught one producing a full-fledged FRB until now. The energy matched, the timing aligned, and suddenly, a key piece of the puzzle snapped into place. But the real revelation lay in the details. Unlike extragalactic FRBs, which often appear as lone, unexplained flashes, this Milky Way burst gave astronomers a front-row seat to its entire life cycle. They watched as the magnetar's twisting magnetic field lines snapped like overstretched rubber bands, releasing enough energy to light up our galaxy's radio sky. Yet this burst was surprisingly weak compared to its extragalactic cousins, just a fraction of their power. That raised a chilling question. If a quiet magnetar in our galaxy could produce an FRB, what kind of unimaginable cosmic monsters were behind the far more powerful bursts from distant galaxies? Some scientists argue that SGR 1935+2154 was merely clearing its throat, a preview of what magnetars can do under extreme conditions. Others speculate that truly colossal FRBs might require something even wilder, like a magnetar colliding with another neutron star or getting sucked into a black hole. But one thing became undeniable after this detection. Magnetars are at least one engine behind these cosmic firecrackers. The discovery didn't solve the FRB mystery, it deepened it, proving that the universe has more than one way to scream across the void. And if magnetars in our own galaxy can behave this unpredictably, what other surprises are lurking in the darkness beyond? Picture a burst of radio waves so bright, it outshines entire galaxies, yet it traveled halfway across the observable universe to reach us. That's the mind-bending reality of FRB 190523, a fast radio burst traced to a galaxy nearly 8 billion light-years away. At that distance, this signal began its journey when Earth was just a toddler, a planet still dominated by single-celled organisms. The fact that we can detect such a fleeting whisper from the cosmos edge speaks volumes about the staggering power behind these eruptions. Pinpointing the source of FRB 190523 was no small feat. Unlike repeating bursts that give astronomers multiple shots at tracking them, this was a one-time event caught by the Deep Synoptic Array in California, a telescope network designed to hunt these cosmic ghosts. Its extreme distance forced scientists to rule out local explanations instantly. This wasn't some Milky Way hiccup or a nearby neutron star acting up. This was a scream from the ancient universe, a time capsule carrying secrets from an era when galaxies were still assembling themselves. The energy required to make a burst visible across 8 billion light-years is almost incomprehensible. In milliseconds, FRB 190523 released as much energy as 500 million suns. That's not a typo, 500 million. To put that in perspective, if you could somehow bottle that energy, you'd have enough power to run human civilization at its current level for trillions of years. Whatever created this burst didn't just break the cosmic sound barrier, it shattered it. But here's the twist: the galaxy hosting this burst isn't what astronomers expected. Unlike the chaotic dwarf galaxies home to many repeating FRBs, this one is a quiet, mature spiral, not the kind of place you'd expect to birth such a violent event. That mismatch hints at something crucial. Fast radio bursts might not have a single origin story. Some could come from magnetars, others from colliding neutron stars, and perhaps some from phenomena we haven't even imagined yet. The vast distances these signals cross also make them cosmic probes. As FRBs travel through space, their waves interact with the sparse electrons between galaxies, slowing just slightly, a delay called dispersion. By measuring this fingerprint, scientists can map the invisible material strewn across the universe's scaffolding. Each burst is like a flashlight beam passing through fog, revealing hidden structures we'd never see otherwise. Yet the very thing that makes FRBs valuable, their unimaginable distances, also makes them fiendishly hard to study. A burst from 8 billion light-years away arrives as a faint, scrambled whisper, its details blurred by eons of travel. It's like trying to reconstruct a symphony from a single note played through a broken telephone. New telescopes like the Square Kilometre Array promise to change that, offering the sensitivity to catch these whispers clearer and farther than ever before. What's truly humbling is realizing how much of the universe's violence goes unseen. For every FRB we detect, thousands likely flash in directions we're not watching, or at times our telescopes aren't listening. These bursts remind us that the cosmos is far from quiet. It's a raging ocean of energy, and we're only beginning to dip our toes into its depths. For decades, astronomers faced a cosmic accounting problem. About half the normal matter in the universe seemed to be missing. This wasn't dark matter, but the ordinary protons and neutrons that make up stars, planets, and us. Theory predicted it should exist, but telescopes couldn't find it. Enter fast radio bursts, the universe's perfect measuring sticks. When these bursts race through space, they carry a hidden record of every electron they've encountered along the way, turning each FRB into a cosmic probe for the invisible stuff between galaxies. The key lies in something called dispersion. As an FRB travels through space, its higher frequency radio waves zip ahead slightly, while lower frequencies lag behind. This happens because electrons in intergalactic space act like tiny speed bumps, slowing the waves down, and the more electrons the burst passes through, the greater the delay. By measuring this smear in the signal, astronomers can count the total electrons along the burst's path like mile markers on a highway. Here's where it gets revolutionary. Most telescopes can only see matter when it's glowing stars, gas clouds, or glowing plasma. But the universe's missing atoms are thought to be hiding as a diffuse fog of warm gas between galaxies, too spread out to emit light yet too hot to absorb it. Traditional instruments are blind to this ghostly material, but FRBs aren't. Their dispersion measures act like cosmic scales, weighing the electrons in this invisible web. Early results are staggering. One study using just a handful of bursts found more matter in the voids between galaxies than expected, exactly where the missing atoms were predicted to lurk. It's as if the universe left its fingerprints on these radio waves, and we're only now learning how to read them. Some astronomers estimate that mapping enough FRBs could finally balance the universe's ledger, accounting for every last proton that's been hiding in plain sight. But the implications go deeper. This intergalactic material isn't just idle fog, it's the fuel for future galaxies, the raw ingredients of cosmic evolution. By tracing its distribution with FRBs, we're effectively charting the universe's circulatory system, understanding how matter flows from emptier regions into the dense nodes where galaxies form. Each burst offers a snapshot of this sprawling network, helping us piece together how the cosmos builds its largest structures over billions of years. What makes this detective work so powerful is its simplicity. Unlike complex simulations or indirect measurements, FRBs give us a direct, clean readout of the universe's hidden scaffolding. They're not just mysterious signals to decode their flashlights illuminating the dark corners of the cosmos, revealing a universe far richer and more intricate than we ever imagined. And with every new burst detected, we get one step closer to solving one of astronomy's longest-standing mysteries. Most fast radio bursts carry the signature of an epic journey, billions of light years etched into their dispersed waves. But a handful break the mold, arriving with suspiciously crisp signals that suggest they barely traveled at all. Take FRB 110214, a burst that showed up with a dispersion measure so low it raised eyebrows across astronomy circles. Instead of the usual stretched-out smear from crossing intergalactic space, this one looked almost like it came from next door, cosmically speaking at least. What makes these low-dispersion bursts so puzzling is their defiance of expectations. If most FRBs are intergalactic fireworks, why do some act like they're from our galactic neighborhood? One possibility is that these oddballs originate in environments choked with magnetic fields so intense, they compress the burst's radio waves, counteracting the usual dispersion. Imagine shouting into a hurricane. Your voice might not carry far, but right where you're standing, it's crystal clear. That's what might be happening near Magnetars with record-breaking magnetic fields where the chaos is so extreme, it bends the rules of how radio waves travel. Another theory suggests these bursts aren't nearby at all, they're just taking a shortcut. Some cosmological models propose that if an FRB passed through a dense filament of the cosmic web or skimmed the edge of a galaxy cluster, its dispersion could appear artificially low, like a hiker's GPS glitching in a canyon. It's a cosmic magic trick. The burst isn't actually close, but the universe's hidden structures make it look that way. Then there's the tantalizing and controversial idea that low dispersion FRBs represent something entirely new. Not magnetars, not collisions, but an undiscovered phenomenon lurking in the spaces between known physics. Could these bursts be the fingerprints of primordial black holes, speculative quark stars, or even defects in the fabric of spacetime itself? Every anomaly like FRB 110214 forces us to question whether we've been too quick to pigeonhole these signals into neat categories. The debate over these outliers isn't just academic, it's a referendum on how well we truly understand the cosmos. If even a few low-dispersion bursts defy explanation, they could be the key to unlocking entirely new chapters in astrophysics. After all, some of science's greatest breakthroughs started with someone asking, "Wait, why doesn't this fit?" Right now, these strange signals are the universe's way of whispering that there's still so much we don't know. And that's what makes them irresistible. Some fast radio bursts flash like cosmic camera strobes here and gone before you can blink. But FRB 181112 takes speed to another level entirely. This record-breaking signal didn't just last milliseconds, its individual bursts were shorter than 1,000th of that time, flashing by in mere microseconds. At that timescale, the entire burst would be over before the blink of an eye even begins. Detecting something this fast pushes radio telescopes to their limits. Most instruments are designed to catch millisecond events, so a microburst like this slips through unnoticed unless the timing is perfect. It's like trying to photograph a bullet mid-flight with a camera set for sunset landscapes. You'd never catch it without specialized equipment. That's why FRB 181112 was only spotted when astronomers combed through raw data with ultra-high-resolution software, revealing bursts so brief they'd been written off as noise. The brevity of these microbursts isn't just a detection challenge, it's a clue. Such sharp, needle-like pulses suggest an emission mechanism far more focused than the messy aftermath of a stellar collision. Imagine the difference between a lightning bolt and a laser. One is a chaotic explosion of energy, while the other is a precision beam. The microsecond structure of FRB 181112 points to something in that laser-like category, possibly a tightly wound magnetic process near a neutron star's surface, or even a beam sweeping past us like a lighthouse with an impossibly fast spin. What's even more fascinating is what we don't see. Unlike repeating FRBs that leave behind an echo of lower frequency radio waves, this microsecond burst was clean, no lingering afterglow, no secondary pulses. That absence hints at an emission process with almost surgical efficiency, converting energy into radio waves with minimal waste. Some theorists suggest this could mean the burst was generated in an unusually clean environment, perhaps far from the turbulent plasma clouds that distort longer FRBs. Yet the biggest mystery remains how something can pack such staggering energy into a window of time barely long enough for light to cross a city block. If a typical FRB is the cosmic equivalent of detonating a nuclear bomb, then FRB 181112 is like concentrating that same energy into the tip of a needle. Whatever's behind these microbursts isn't just powerful, it's operating on scales and speeds we've yet to fully comprehend. And if we've only just started catching these ultra-fast whispers, how many more are out there hiding in the static of the universe? When a fast radio burst named FRB 180301 flashed its polarized signal at Earth, it didn't just deliver energy, it smuggled out classified intel about its cosmic prison. Polarization, the hidden fingerprint of how radio waves twist and align, is like a secret language written into these bursts, revealing details about the extreme environments they escape from. This particular burst arrived with its radio waves sharply twisted, a telltale sign it had fought its way through some of the most brutal magnetic fields in the universe. The key lies in understanding how polarization works. Imagine radio waves as vibrating ropes. If they oscillate in a single plane like a jump rope, that's linear polarization. But if the wave spirals like a corkscrew, it's circularly polarized. FRB 180301 showed both. Its waves first forced into alignment by intense magnetic fields, linear before being violently twisted circular on their way out. This double signature is the smoking gun of a magnetar's influence, where magnetic fields are so powerful they can rearrange the very fabric of space around them. What makes these polarized bursts so valuable is their ability to act as cosmic magnetic probes. As radio waves traverse magnetized plasma, their polarization gets sculpted by the field's strength and structure, a process called Faraday rotation. By decoding these twists, astronomers can effectively X-ray the invisible magnetic environment surrounding the burst source. In the case of FRB 180301, the polarization was so extreme, it suggested magnetic fields thousands of times stronger than those near Earth, a neutron star's brutal neighborhood where even atoms stretch into needle-like shapes. But polarization doesn't just expose magnetic monsters, it also chronicles the journey these bursts take. Some FRBs emerge with pristine, undisturbed polarization, implying they traveled through relatively clean intergalactic space. Others arrive scrambled, their waves twisted by turbulent plasma clouds or the disordered magnetic fields of galaxy clusters. It's as if each burst carries a travel diary, documenting every magnetic storm and cosmic whirlpool it passed through on its way to us. The real puzzle: not all repeating FRBs show the same polarization signatures, even when they come from the same source. Some bursts from FRB 121102, for example, flip between being highly polarized and completely unpolarized, as if something in their local environment is switching between order and chaos. One theory suggests this could be due to a magnetar's magnetic field lines tangling and snapping like a phone cord wound too tight, creating temporary zones of extreme turbulence. There's even wilder speculation among theorists. The rare bursts with near-perfect circular polarization, those tight corkscrew waves, might hint at something more exotic than neutron stars. Could they originate from regions where space-time itself is twisted, like the ergosphere of a rapidly spinning black hole, or perhaps from quantum anomalies in hypothetical action stars? The data isn't conclusive yet, but every new polarized burst chips away at the mystery, proving these signals aren't just cosmic flukes. They're encrypted messages from the universe's most extreme frontiers. As telescopes grow more sophisticated, polarization is becoming the Rosetta Stone for decoding FRBs. Future observatories like the Square Kilometre Array won't just detect these bursts, they'll dissect their polarization with forensic precision, mapping magnetic fields across billions of light years. Each twisted radio wave is a thread in the universe's grand magnetic tapestry, and we're just beginning to pull on the strings. Among the many mysteries of fast radio bursts, perhaps none is more perplexing than the case of the dark ones, bursts like FRB 150215 that scream across the cosmos in radio waves but leave no trace in any other part of the electromagnetic spectrum. When this particular burst flashed into existence in 2015, telescopes scrambled to catch its afterglow in visible light, X-rays, even gamma rays. Yet despite its staggering energy, enough to power Earth for centuries, it vanished without a whisper in any other wavelength. This wasn't just a cosmic oddity. It was a direct challenge to everything we thought we knew about how these bursts work. The absence of multi-wavelength signals is more than just puzzling. It's a fundamental roadblock in our understanding. Most known cosmic explosions, from supernova to neutron star collisions, light up like fireworks across multiple frequencies. Even magnetar flares, the leading suspects behind many FRBs, typically blast out X-rays alongside their radio signatures. So why would some bursts go radio dark? One possibility is that these dark FRBs originate in environments so extreme they suppress other forms of radiation. Imagine a neutron star shrouded in a thick cocoon of plasma radio waves might escape, but higher energy photons get absorbed before they can travel far. Or consider an even stranger scenario. What if dark bursts don't come from magnetars at all? Some theorists speculate they might be the product of exotic, low-density regions of space cosmic voids where matter is so sparse there's hardly any material to heat up and glow in X-rays or visible light. In these ghostly neighborhoods, a collapsing star or a black hole's sudden energy release might produce a clean radio burst without the usual electromagnetic pollution. It's like hearing an explosion in an empty warehouse. You'd get the sound, but no flash or smoke to tell you what caused it. The implications are profound. If dark FRBs truly emerge from these cosmic deserts, they could be mapping regions of the universe that telescopes normally can't see, vast, empty stretches where galaxies are few and far between. That would make them unique probes of the universe's large-scale structure, highlighting not just where matter clusters, but where it's conspicuously absent. Yet the mystery deepens when we look at FRB 150215's other quirks. Unlike many bursts, its radio signal showed almost no distortion from traveling through interstellar or intergalactic material, as if it took a nearly clean path to Earth. That could mean it comes from a relatively uncluttered region of space, or that whatever produced it did so in a way that kept the signal unnaturally pure. Some researchers float the idea of naked magnetars, neutron stars floating far from the gas clouds that usually surround them, allowing their radio bursts to escape pristine. Others wonder if we're seeing an entirely new class of FRBs, one governed by physics we haven't yet uncovered. The enigma of dark bursts forces us to confront how much we still don't understand about these cosmic flashes. Every time we think we've pinned down their origins, the universe throws us a curveball, a burst that defies the pattern, leaving us with more questions than answers. And until we catch one of these dark FRBs in the act with every instrument at our disposal, their secrets will remain locked away, hidden in the voids between the stars. The idea that fast radio bursts might be more than natural cosmic phenomena, that they could be evidence of advanced alien technology, is the kind of hypothesis that sends shivers down the spine. It's also one that splits the scientific community right down the middle. On one side, skeptics dismiss it as sensationalism, while on the other, a handful of researchers argue we'd be foolish to ignore the possibility entirely. After all, if an extraterrestrial civilization wanted to announce its presence or even power interstellar spacecraft, wouldn't a brief, incredibly energetic radio burst be an efficient way to do it? The logic behind the alien propulsion theory is startlingly simple. Some FRBs pack enough energy in milliseconds to rival the sun's output for days, energy that, if harnessed, could theoretically push light sails across galaxies. In 2017, Harvard astronomers Loeb and Lingham even calculated that a solar-powered transmitter the size of a planet, focusing a beam through an enormous dish, might produce signals matching FRB characteristics. The burst's fleeting nature would make them efficient for communication too, like cosmic Morse code blasted across the void. But before we rewrite the history books, there's a mountain of skepticism to scale. The vast majority of FRB researchers point out that nature has no shortage of ways to generate extreme radio flashes without invoking aliens. Magnetars, colliding neutron stars, and even evaporating black holes all fit the bill without requiring intelligent intervention. The repeating patterns in some FRBs, often cited as potential signatures, also appear in purely natural phenomena like pulsars, which have spun with clockwork regularity for decades without anyone suspecting extraterrestrial engineers. Perhaps the most damning evidence against the alien hypothesis is sheer statistics. FRBs arrive from all directions and distances, some from galaxies billions of light-years away. If these were alien beacons or propulsion beams, we'd have to assume civilizations arose independently at roughly the same cosmic time across the universe, all choosing the same cryptic way to signal. That stretches coincidence beyond plausibility for most scientists, yet the debate isn't entirely one-sided. The infamous WOW signal of 1977 reminded us that cosmic radio anomalies can defy explanation for decades. And some FRB properties, like their bafflingly efficient energy emission or the sporadic repetition in seemingly unnatural intervals, still lack airtight natural explanations. Even SETI researchers, who typically avoid sensational claims, admit FRBs deserve a place in the search for extraterrestrial intelligence, if only to rule out the extraordinary. What makes this tension fascinating is how it reflects science at its most self-correcting. The alien hypothesis, however unlikely, forces astronomers to sharpen their arguments and seek better evidence. Every new repeating burst, every polarized signal, and every multi-wavelength observation chips away at the uncertainty. For now, Occam's razor favors natural origins, but in a universe as vast and strange as ours, closing the door entirely on wonder might be the riskiest assumption of all. The discovery of FRB 110523 lurking near a supernova remnant sent shockwaves through the astronomy community, not just because of the burst itself, but because of where it seemed to call home. Supernova are nature's most violent explosions, capable of forging neutron stars or black holes in their cores. Could these catastrophic events also be the birthplaces of fast radio bursts? The tantalizing proximity of this particular burst to a stellar graveyard reignited a debate that cuts to the heart of FRB origins. Are we seeing cosmic causation, or just a fleeting alignment of unrelated phenomena? Supernovae have long been suspected as potential FRB factories. When a massive star collapses, it doesn't just leave behind a glowing remnant. It can create a magnetar, a neutron star with a magnetic field so intense it could power FRBs like a cosmic particle accelerator. The case for this connection grew stronger when astronomers noticed that FRB 110523's host environment matched the chaotic aftermath of recent stellar explosions. Gas clouds still reeling from the supernova's shockwave, swirling with heavy elements forged in the dying star's core. This was exactly the kind of turbulent nursery where a newborn magnetar might lurk. But correlation doesn't always mean causation. Skeptics point out that supernova remnants are common, especially in star-forming galaxies where FRBs tend to appear. The probability of a chance alignment isn't negligible, like finding a lightning strike near a tree without proving the tree attracted the bolt. What's more, the dispersion measure of FRB 110523 suggested it traveled through significantly more material than expected if it originated in the nearby remnant, implying its true source might lie far beyond, merely appearing close by cosmic coincidence. The plot thickened when astronomers examined the burst's polarization. Unlike the clean signals from some magnetar-associated FRBs, this one arrived scrambled, its radio waves twisted by dense magnetic fields, exactly what you'd expect if it had plowed through the turbulent wreckage of a supernova. This fingerprint hinted that even if the burst didn't come from the remnant itself, it might have traversed the remnant's chaotic outskirts, picking up telltale distortions along the way. The debate mirrors an older astronomical puzzle: the link between supernova and gamma-ray bursts. For years, scientists debated whether these two phenomena were connected until observations finally confirmed that certain supernova could indeed trigger gamma-ray bursts under extreme conditions. Could FRBs represent a similar cosmic partnership, one where only specific types of supernova, under rare circumstances, give rise to radio-bright offspring? The answer might lie in the details of stellar collapse. Not all supernova create magnetars, and not all magnetars may produce FRBs. The critical factor could be the speed of the progenitor star's rotation. A rapidly spinning core might amplify magnetic fields to FRB-capable strengths during collapse. Until we catch a supernova in the act of spawning an FRB, or better yet, witness a magnetar's birth followed by repeating bursts, the connection remains compelling but unproven. Every new FRB found near a supernova remnant adds weight to the theory, while every outlier forces us to reconsider. It's a cosmic detective story where the clues are written in radio waves and stardust, and the final verdict may hinge on the next generation of telescopes catching the universe in the act of creating one of its most mysterious phenomena. Some fast radio bursts arrive not as single, clean pulses, but as a rapid-fire sequence of subbursts, like cosmic echoes bouncing through the void. FRB 160102 is the poster child for this phenomenon, splitting into at least 5 distinct components during its 3-millisecond lifespan. Each sub-burst wasn't just a repeat. It drifted downward in frequency like a bird's chirp, creating a pattern that has astronomers rethinking how these signals interact with the universe on their way to us. This chirping effect offers crucial clues about both the burst's environment and its inner workings. As radio waves travel through space, they encounter clouds of ionized gas, patchy regions where free electrons slow certain frequencies more than others. The drifting sub-bursts in FRB 160102 suggest it plowed through a clumpy interstellar medium, with each component taking a slightly different path through these turbulent electron clouds. It's like shouting into a canyon and hearing your voice bounce off uneven rock faces. The returning echoes carry a map of the terrain they've crossed. But the story doesn't end there. Some theorists argue these multi-component bursts might expose the actual emission mechanism at the source. Imagine a magnetar's crust cracking under intense magnetic stress, not with a single fracture, but a cascade of smaller breaks, each releasing a sub-burst as the star's twisted magnetic field lines snap and reconnect. The downward frequency drift could then reflect how these energy releases propagate through different layers of the neutron star's magnetosphere. with each subsequent burst emerging from deeper, denser regions where plasma interactions shift the radio waves to lower frequencies. There's even a wilder possibility that these subbursts are evidence of cosmic lenses. Just as light bends around massive objects, intense gravitational fields near neutron stars or black holes could split a single FRB into multiple components, each following a slightly different spacetime path to Earth. If true, this would make FRB 160102 not just a signal, but a gravitational fingerprint, a chance to measure warped space around distant compact objects using radio waves as our probe. Yet the most intriguing aspect might be what these multi-component bursts don't do. Unlike repeating FRBs with erratic patterns, FRB 160102's subbursts followed a near-perfect mathematical progression in their time and frequency spacing. That kind of order amidst chaos hints at an underlying physical process governed by precise rules. Whether it's the quantum oscillations of a magnetar's crust, the resonant frequencies of plasma clouds surrounding a black hole, or something entirely undiscovered. Every new multi-component burst adds another layer to the mystery. Are we hearing the universe's most extreme objects ring like bells, their vibrations translated into radio chirps? Or are these signals being sculpted by invisible cosmic obstacles on their billion-year journeys? The answers may lie in the subtle gaps between those sub-burst silent intervals that could hide the secrets of everything from neutron star physics to the distribution of matter in the emptiest reaches of intergalactic space. One thing's certain, when an FRB breaks into pieces, those fragments aren't just noise, they're pieces of a puzzle we're only beginning to assemble. Strangely enough, there's a dead zone in the fast radio burst spectrum, a quiet gap between 700 and 900 megahertz where these cosmic flashes almost never appear. This eerie silence, known as the FRB wall, isn't just a curiosity, it's a potential Rosetta Stone for understanding whether we're missing bursts due to our telescope's blind spots or if the universe itself is filtering them out. At first glance, the gap seems like a technical glitch. After all, radio telescopes aren't perfect. They have frequency ranges where they're more sensitive, and others where interference or hardware limitations create dropouts. But here's the twist. Even when astronomers stitch together observations from multiple instruments covering the full spectrum, that stubborn, quiet patch remains. It's as if FRBs actively avoid those frequencies, like radio ghosts unwilling to cross some invisible cosmic threshold. One compelling theory suggests this gap isn't about the bursts themselves, but about what stands between them and us. Interstellar and intergalactic space isn't empty, it's frothy with ionized gas that absorbs specific radio frequencies. The 700 to 900 megahertz range might overlap with a resonance frequency where electrons in these plasma clouds efficiently soak up radio waves, creating a natural shadow zone. If true, the wall isn't a lack of FRBs, it's a cosmic curtain, hiding bursts that are actually there but get swallowed before reaching Earth. Then there's the wilder possibility that the wall reveals something fundamental about how FRBs are born. Magnetars, the leading suspects behind these bursts, often emit radio waves through processes involving plasma oscillations and magnetic reconnection. These mechanisms naturally favor certain frequency bands, potentially skipping others altogether. Picture a piano where some keys simply don't produce sound, not because they're broken, but because the instrument's physics don't allow vibrations at those exact pitches. But the plot thickens when you consider that a handful of bursts have pierced the wall, like FRB 180916's faint whispers detected at 800 megahertz. These rare exceptions might be the key. If most bursts vanish in this range but a few slip through, it could mean the wall isn't absolute, just a statistical dip caused by an emission process that makes mid-frequency bursts intrinsically rarer. The implications ripple outward. If the wall is instrumental, we need better telescopes. If it's astrophysical, it could map hidden structures in the cosmic web. And if it's intrinsic to FRBs, that might be the most exciting scenario of all, a clue that these bursts aren't just louder versions of known phenomena, but something entirely new, playing by rules we've yet to decipher. Until we crack this silent code, the wall remains one of the universe's most enigmatic radio silences. Fast radio bursts don't just appear randomly across the cosmos, they emerge from galaxies as diverse as the bursts themselves. Some blast out from tiny, chaotic dwarf galaxies barely a fraction the size of the Milky Way, while others originate in massive, sedate ellipticals where star formation ceased eons ago. This galactic variety isn't just a curiosity, it's a vital clue in unraveling what exactly creates these explosive radio flashes. Take FRB 121102, the first repeater ever discovered. Its home is a dwarf galaxy 3 billion light-years away, a place buzzing with stellar birth and death. Gas clouds collide, young stars ignite, and supernova rock the neighborhood, exactly the environment you'd expect to forge magnetars, the ultramagnetic neutron stars suspected of powering many FRBs. Yet contrast that with FRB 180924, a burst traced to a far more tranquil setting. A massive spiral galaxy resembling the Milky Way, where star formation ticks along at a leisurely pace. How could two such different galactic environments produce such similar radio explosions? The answer might lie in the life cycles of stars. Dwarf galaxies, despite their small size, are stellar factories, churning out massive stars that live fast and die young. When these giants collapse, they often leave behind magnetars, neutron stars born spinning furiously with magnetic fields that could power FRBs. But in quieter galaxies like the host of FRB 180924, the story could be different. Perhaps these bursts come from older, recycled magnetars, neutron stars that gained a second lease on life by siphoning material from a companion star, revving up their magnetic fields enough to occasionally unleash a burst. Then there are the true oddballs like FRB 190523's host a massive elliptical galaxy where star formation effectively ended billions of years ago. These cosmic retirement communities shouldn't have the young, massive stars needed to create traditional magnetars. One possibility is that the bursts there come from collisions, white dwarfs or neutron stars crashing together in the crowded galactic core, creating one-time blasts rather than repeaters. Or perhaps even dormant galaxies hide a few exotic stellar remnants capable of unpredictable violence. The variety extends beyond galaxy types. Some FRB hosts, like the dwarf home of FRB 180916, show signs of recent mergers, galactic pileups that trigger bursts of star formation. Others sit in relative isolation, their bursts emerging from calm, undisturbed neighborhoods. This inconsistency forces astronomers to consider whether FRBs might have multiple formation paths. Maybe some come from young magnetars in star-forming regions, while others arise from older, more scattered neutron stars activated by rare cosmic events like a chance encounter with a rogue black hole or a sudden influx of interstellar material. Every new host galaxy identified adds another piece to this cosmic jigsaw. Why do some turbulent dwarf galaxies produce both repeating and one-off bursts, while serene spirals seem to favor one-time events? Why do a few FRBs appear to originate far from their host galaxy's bright core, lingering in the dim outskirts where few stars exist? The answers might rewrite not just our understanding of FRBs, but of how galaxies nurture or suppress the most extreme phenomena in the universe. Each burst is a messenger carrying not just the signature of its birth, but the imprint of the galactic environment that shaped it. And as we map more of these hosts, we're beginning to see a pattern emerge, one where the universe has more than one way to scream across the void. The sheer energy behind fast radio bursts defies comprehension. A single millisecond flash like FRB 150807 can unleash as much power as the sun radiates over 80 years. That's not a typo. 80 years of sunlight compressed into the time it takes a hummingbird to flap its wings once. To grasp the scale, imagine every star in the Milky Way focusing their combined energy into a pinpoint beam for the briefest instant. That's the incomprehensible firepower we're dealing with. The numbers alone are staggering. When astronomers calculated FRB 150807's luminosity, they found its equivalent isotropic energy. The total power, if emitted equally in all directions, reached 10 to the 34 ergs. To put that in perspective, that's 100,000 times more energetic than the most powerful solar flares ever recorded. And unlike solar flares that dissipate slowly, FRBs channel all that energy into radio frequencies with almost impossible efficiency, as if nature itself has mastered the art of cosmic laser beams. But where could such concentrated energy possibly come from? Magnetar hyperflares currently top the suspect list. These apocalyptic eruptions occur when a neutron star's crust, strained by unimaginable magnetic fields, suddenly snaps, unleashing pent-up energy as the star's magnetic lines violently reconnect. Picture Earth's strongest earthquake, then multiply its power by a quadrillion and confine it to a city-sized object. The problem: even the mightiest magnetar flares observed so far fall short of FRB energy budgets by a factor of 1,000. Unless we're missing an entire class of supermagnetars with even more extreme physics, something doesn't add up. That gap has led theorists to consider even more cataclysmic scenarios like neutron star collisions. When two of these ultra-dense corpses spiral together, their merger can trigger gravitational waves, gamma-ray bursts, and potentially FRBs as their magnetospheres briefly intertwine. The math almost works. A merger's magnetic field could theoretically concentrate energy into a narrow beam, amplifying its brightness when aimed at Earth. But collisions are one-time events, leaving us with another puzzle: how to explain repeating FRBs if their power sources destroy themselves upon activation. Perhaps the answer lies in hybrid models. Some researchers propose blitzar events, neutron stars so massive they should collapse into black holes but are temporarily held up by rapid rotation. When they finally succumb, their dying magnetic fields could twist into an FRB-producing configuration. Others speculate about neutron star lightning, and discharges from charged particles accumulating in magnetar atmospheres until they erupt like a cosmic-scale capacitor explosion. The most tantalizing possibility: that we're seeing entirely new physics, quantum vacuum breakdowns, cosmic strings snapping, or even primordial black holes evaporating, all remain wild but mathematically plausible contenders. Each new ultra-energetic burst chips away at our assumptions, proving the universe has energy reservoirs we've yet to imagine. Until we catch one of these cosmic powerhouses in the act, the energy puzzle remains wide open, a reminder that for all our knowledge, the cosmos still holds cards it hasn't shown us. The universe speaks in many languages. Some whisper through gravity, others shout in radio waves. What if the most powerful fast radio bursts aren't just cosmic radio stations, but also gravitational fireworks? The tantalizing possibility that FRBs might coincide with gravitational wave events bridges two of astronomy's most exciting frontiers, suggesting these enigmatic bursts could be the multi-messenger equivalent of a cosmic fireworks finale. Gravitational waves, ripples in space-time caused by cataclysmic events like merging black holes or neutron stars, travel at light speed, just like FRBs. When two neutron stars collided in 2017, producing both gravitational waves and a gamma-ray burst, astronomers wondered, could similar collisions also trigger FRBs? The math is seductive. As neutron stars spiral together, their magnetospheres could violently interact, launching relativistic shocks capable of powering both gravitational waves and a focused radio beam detectable across the universe. Yet despite extensive searches, no FRB has ever been definitively linked to a gravitational wave event. the reasons for this absence might lie in the extreme conditions required. For an FRB to coincide with gravitational waves, the merging neutron stars would need to have ultra-strong magnetic fields, perhaps one or both being magnetars, to funnel enough energy into radio waves. Most detected mergers so far involve neutron stars with relatively tame magnetic fields, better at producing gamma rays than FRBs. It's like expecting a lightning bolt from a matchstick. The energy just isn't configured the right way. Another hurdle is timing. Gravitational wave detectors like LIGO and Virgo scan the whole sky, but they're blind to a burst's direction unless multiple observatories catch it. FRB telescopes, meanwhile, pinpoint locations with precision, but only see a tiny slice of the sky at once. The odds of both instruments catching the same event simultaneously are staggeringly low, like two flashbulbs popping in a stadium at the exact same moment, with only one camera pointed in the right direction. Even if an FRB and gravitational wave did occur together, we might miss the connection simply because our instruments weren't aligned to see both, but the search is far from over. Upcoming gravitational wave detectors, like the space-based LISA mission or next-gen ground observatories, will expand our sensitivity to neutron star mergers. Radio telescopes, meanwhile, are growing faster and more agile, with some now capable of automatically swiveling toward gravitational wave alerts within seconds. Even more intriguing are speculative models suggesting delayed FRB signals that might emerge hours or days after a merger, as a newborn magnetar's magnetic field reorganizes or a black hole's accretion disk settles. The absence of coincident detection so far isn't necessarily a dead end. It might simply mean we're looking for the wrong combination of events, or that the universe hasn't yet offered up the perfect specimen for study. Every new gravitational wave detection brings us closer to the moment when, perhaps, the cosmos will decide to synchronize its signals, blending the warping of space-time with a scream of radio energy that leaves no doubt. These phenomena are two sides of the same celestial coin. Until then, the silence between the signals is just another mystery waiting to be broken. Hunting for fast radio bursts doesn't end when the radio waves fade. Astronomers desperately search for afterglows, lingering fingerprints of these explosions in X-rays, visible light, or even gamma rays. But here's the frustrating truth. Most bursts vanish without a trace in other wavelengths, leaving researchers staring at empty patches of sky where theory insists something should be glowing. The few exceptions, like FRB 200428's paired X-ray burst, aren't just victories, they're masterclasses in how much we've misunderstood about these cosmic enigmas. The challenge begins with the sheer speed of FRBs. Lasting mere milliseconds, their afterglows, if they exist at all, must be caught within seconds before dissipating into the void. Telescopes like Swift and Chandra lurk in standby mode, ready to pivot toward fresh bursts at a moment's notice. Yet despite countless rapid response observations, most come up empty. One leading theory suggests that the radio burst might be the tip of an iceberg, a narrow, focused beam where most energy escapes as invisible particles or low-frequency waves our instruments can't detect. It's like searching for a flashlight's glow by only staring directly at the bulb. Unless you're in the beam's path, you'll see nothing. FRB 200428 shattered this pattern. When this Milky Way magnetar erupted in April 2020, it didn't just emit a radio burst, it unleashed a simultaneous X-ray flare bright enough to blind sensors. For the first time, astronomers witnessed an FRB's multi-wavelength counterpart, proving at least some bursts to have visible partners. But there was a catch. The X-ray emission was 1,000,000 times more energetic than the radio component, a mismatch that left theorists scrambling. If this was the template, why hadn't earlier searches spotted similar X-ray flashes? The answer might lie in geometry and distance. FRB 200428's X-rays sprayed in all directions while its radio signal was tightly beamed, meaning even if an X-ray afterglow exists, we'd only detect it for nearby bursts where the spray reaches Earth. For distant extragalactic FRBs, the X-rays could be too diluted by the time they cross billions of light years. That would make FRB 200428 a cosmic unicorn, close enough for its full fury to be visible, but rare enough to explain why similar detections remain elusive. Then there's the puzzle of optical afterglows, the holy grail for amateur astronomers hoping to spot FRB remnants with backyard telescopes. While a few claims have surfaced, like a faint flicker coinciding with FRB 131104, none have been conclusively confirmed. The energy required to make a visible glow at intergalactic distances would dwarf even the radio burst itself, suggesting that if optical counterparts exist, they're either exceptionally faint or blink out before telescopes can swivel into position. Rarest of all are gamma-ray counterparts. The Fermi Space Telescope once caught a weak gamma-ray flash near an FRB's location, but the timing was too uncertain to confirm a link. If verified, such a connection would imply some bursts tap into particle acceleration processes rivaling supernova, perhaps from magnetars undergoing crustal quakes so violent they ripple spacetime itself. Every failed afterglow search is its own kind of data point, narrowing the possibilities for how these bursts operate. The absence of X-rays from most repeating FRBs hints their energy might be funneled purely into radio waves like cosmic lasers fine-tuned to a single frequency. Meanwhile, the few multi-wavelength detections we do have suggest there's no one-size-fits-all model. Some bursts emerge from messy, multi-frequency explosions, while others are radio-only virtuosos. The afterglow hunt is far from over. Next-generation telescopes like the Vera Rubin Observatory promise to scan the skies with unprecedented speed, potentially catching elusive optical counterparts. And with every new magnetar flare detected in our galaxy, astronomers edge closer to understanding whether FRB 200428 was a fluke or a sign that we've been missing half the show all along. Until then, each empty patch of sky whispers the same tantalizing question: what invisible fireworks accompany these radio screams from the dark? Among the symphony of fast radio bursts, some arrive not as sharp clicks but as drawn-out echoes, their signals stretched and smeared by the cosmic static of interstellar space. FRB 190611 is the poster child for this phenomenon. Its once crisp millisecond pulse stretched into a faint, scattering tail that lingers like reverberations in a galactic canyon. This distortion isn't just noise, it's a forensic record of every turbulent plasma cloud the burst traversed on its billion-year journey to Earth. The physics behind scattering is deceptively simple. As radio waves plow through the sea of electrons filling interstellar and intergalactic space, they don't travel in straight lines. They ricochet off density fluctuations in the plasma, like light shimmering through hot asphalt. Each detour adds a tiny delay, with lower frequency waves scattering more than higher ones. The result, a burst that should have arrived as a single spike instead smears across milliseconds or even seconds, its energy dispersing into a characteristic downward drift. The longer the tail, the rougher the terrain the signal crossed. FRB 190611's extreme scattering was the smoking gun. Unlike bursts from relatively clean intergalactic highways, this one's extended wake suggested it had traversed a cosmic obstacle course. Dense filaments of ionized gas, turbulent supernova remnants, or perhaps the magnetized outskirts of galaxy clusters. When astronomers traced its origin to a distant spiral galaxy, the pieces fit. Its path likely grazed that galaxy's bustling star-forming regions, where newborn stars and supernova churn the interstellar medium into frothy chaos. But here's where it gets revolutionary. By measuring the exact shape and duration of scattering tails, scientists can reconstruct the hidden structure of the universe's matter distribution in 3D. Think of it like sonar for the cosmos. Each smeared burst reveals the texture of otherwise invisible plasma clouds along its line of sight. Some bursts show multiple scattering components, hinting at discrete layers of turbulence, perhaps the combined effect of passing through a host galaxy's interstellar medium, then the diffuse halo of a foreground galaxy, before finally punching through the Milky Way's own turbulent outskirts. The most intriguing cases are bursts with extreme scattering like FRB 180924b, whose signal stretched across nearly a second despite originating billions of light-years away. Such severe distortion points to environments far wilder than typical interstellar space. One theory suggests these bursts skim the dense, magnetized bubbles around quasars or active galactic nuclei, where plasma swirls at nearly light speed. Others propose they've traversed the wakes of ancient galaxy collisions, where ejected gas has had eons to develop fractal-like turbulence on scales from light-years down to kilometers. There's even a tantalizing cosmological twist. The amount of scattering should increase with distance. The farther a burst travels, the more electron clouds it should encounter. Yet some nearby bursts show disproportionately heavy scattering, while a few distant ones arrive suspiciously clean. This mismatch might trace back to the universe's expansion. As space stretches, it could be diluting the very turbulence that causes scattering, leaving older bursts from the denser early universe paradoxically less smeared than younger ones cutting through today's sparser cosmic web. What makes scattering more than just an observational headache is its potential to expose the universe's most chaotic neighborhoods, places too diffuse to see with telescopes but turbulent enough to leave fingerprints on passing radio waves. Future arrays like the Square Kilometre Array will transform these distorted tails into high-resolution maps, charting the stormy seas of ionized gas that fill the voids between galaxies. Every smeared burst is a message in a bottle, its wrinkles and creases telling the story of the unseen oceans it crossed to reach us. And sometimes it's in the blur, not the sharp details, that the cosmos reveals its most spectacular secrets. Fast radio bursts play a cosmic game of peekaboo. Most flash once and vanish forever, while a stubborn few repeat like clockwork. This split personality has astronomers locked in debate. Are one-off FRBs the death cries of celestial objects, or are we simply not listening long enough to catch their encores? The answer could rewrite our understanding of how the universe's most extreme phenomena live and die. Take the case of the original Lorimer Burst, a brilliant flash in 2007 that never returned despite years of follow-up observations. If this was a neutron star collision, as some models suggest, its silence makes perfect sense. When two ultra-dense stellar corpses spiral together and merge, the result is apocalyptic, a final, explosive goodbye that leaves behind either a black hole or a hypermassive neutron star too unstable to produce repeat bursts. The energy released could easily power a single, spectacular FRB before fading into oblivion. It's the cosmic equivalent of a microphone dropping out mid-performance, one ear-splitting feedback screech, then silence. Yet Magnetar Flare advocates counter with an unsettling possibility. What if non-repeaters do repeat, just on timescales longer than human patience? Imagine a hyperactive magnetar that erupts every few decades like Yellowstone's supervolcano. Its outbursts are catastrophic but rare. Our telescopes, tuned to scan the skies for years rather than centuries, might miss the pattern entirely. Supporting this, some once dormant magnetars in our galaxy have suddenly reactivated after years of quiet, proving that apparent one-offs can be part of much longer cycles. The plot thickens when you consider selection bias. Repeating FRBs are easier to confirm. Their recurring nature allows precise localization, while single bursts often fade into statistical uncertainty. Could there be an entire population of slow repeaters masquerading as one-offs because we haven't watched their patches of sky long enough? The CHIME telescope's recent discovery of bursts repeating after years of silence suggests we're only scratching the surface of their true cadences. Then there's the middle ground theories proposing that repeaters and non-repeaters share the same engine but differ in their fuel. Perhaps both originate from magnetars, but one-off bursts emerge from younger, more volatile stars that exhaust their magnetic energy in a single outburst, while repeaters come from older, stable systems capable of periodic eruptions. Alternatively, the surrounding environment might dictate behavior. A magnetar floating in sparse interstellar gas might produce isolated bursts, while one embedded in a dense nebula could have constant fuel for repeats. The most radical ideas lurk at the fringes. Could some one-off FRBs be the signature of quantum vacuum decay, a theoretical process where a bubble of true vacuum expands at light speed, rewriting the laws of physics as it goes? Or perhaps they're the last radio screams of primordial black holes evaporating via Hawking radiation, their demise playing out in milliseconds after billions of years of quiet. These scenarios are speculative but underline how profoundly our models might shift with the next detection. What's clear is that the repeater/non-repeater divide isn't just a quirk of observation, it's a fundamental fork in the road for FRB origins. Every new burst that refuses to repeat tightens the case for catastrophic origins, while every surprise recurrence proves the universe still has tricks up its sleeve. Until we catch a neutron-star merger in the act of producing an FRB or witness a known one-off suddenly reignite, this duality will remain one of the deepest mysteries in the cosmos, a reminder that sometimes silence speaks louder than the burst itself. Some theories about fast radio bursts push the boundaries of known physics into territory so strange, it sounds like science fiction. Among the most mind-bending is the idea that FRBs might come from cosmic strings, hypothetical cracks in the fabric of space-time left over from the universe's violent birth. Picture the early cosmos like cooling glass. As it expanded and cooled, imperfections might have formed, one-dimensional filaments of pure energy thinner than a proton but stretching across galaxies. If these strings exist and suddenly snap, the math suggests they could release shockwaves powerful enough to generate an FRB's signature radio scream. The cosmic string model offers elegant solutions to some of FRB's thorniest puzzles. Their mind-boggling energy output, a snapping string, could convert pure space-time tension into radiation with near-perfect efficiency, dwarfing even magnetar flares. The lack of afterglows, unlike stellar explosions, a string's rupture would leave no lingering debris or electromagnetic traces, just a clean, ultra-powerful radio spike. Even the repeater mystery finds an explanation. Cosmic strings might vibrate or develop kinks that trigger repeated bursts as they settle into new configurations. But for all its theoretical appeal, the cosmic string hypothesis walks a tightrope between genius and desperation. The biggest hurdle: we've never definitively detected cosmic strings at all. They're predicted by some unified field theories but remain purely mathematical constructs for now. That's like blaming invisible unicorns for lightning strikes possible, but hardly persuasive without physical evidence. Even if strings exist, their proposed density in the universe suggests snapping events would be vanishingly rare, struggling to account for the hundreds of FRBs we've already catalogued. Critics also point to observational mismatches. Many FRBs show polarization patterns best explained by magnetized plasma, the kind found around neutron stars, not floating space-time defects. And the repeating bursts localization to star-forming galaxies hints at a connection to stellar evolution rather than primordial cosmology. If cosmic strings were responsible, we'd expect FRBs to appear randomly across all galaxy types, even in the emptiest voids where strings should drift undisturbed. Yet the theory isn't ready for the scrap heap. Some FRB oddities resist conventional explanations. The extraordinary purity of certain bursts, their energy concentrated almost entirely in radio frequencies, aligns suspiciously well with cosmic string models predicting narrowband emission. And the rare, ultra-energetic FRBs that defy magnetar energy limits might find their only plausible source in the rupture of spacetime itself. The debate embodies a deeper tension in astrophysics. When confronted with cosmic mysteries, do we exhaustively test mundane explanations before invoking exotic physics? Or does the universe occasionally demand radical ideas to shake us from complacency? For now, cosmic strings remain a tantalizing what-if, a reminder that the true nature of FRBs might be stranger than anything we've dared imagine. Until we catch spacetime itself in the act of unraveling, these hypothetical defects will linger at the fringe, whispering that our map of reality may still have missing continents. The repeating fast radio burst 121102 doesn't just fire off identical signals. Its sub-bursts slide down the radio dial like a cosmic trombone, each subsequent pulse arriving at a lower frequency than the last. This curious frequency drift isn't just aesthetic, it's a coded message about the extreme physics unfolding near the burst source. Picture a handful of pebbles tossed into a pond at slightly different times. The ripples don't align neatly but create an overlapping pattern where each new ring emerges inside the last. That's essentially what happens when we see downward drifting subbursts, except instead of water, we're dealing with relativistic plasma and warp-speed magnetic fields. One compelling explanation ties this drift to the turbulent environment surrounding a magnetar. As magnetic field lines snap and reconnect near the neutron star's surface, they could generate multiple radio-emitting shocks at different altitudes in the magnetosphere. Higher frequency radio waves might form closer to the surface where plasma is denser, while lower frequencies emerge farther out where conditions are more diffused. If these shocks occur in rapid succession, moving outward from the star, the resulting burst would naturally cascade downward in frequency like a musical chord played from top to bottom instead of all at once. Then there's the plasma lensing theory, which flips the script entirely. Instead of the emission mechanism creating the drift, the signal might be getting distorted on its way to us. Imagine an FRB passing through bubbling clouds of magnetized plasma near its source. These chaotic structures could act like cosmic prisms, bending different radio frequencies by varying amounts. Higher frequencies might slip through relatively unscathed, while lower ones take detours, arriving slightly delayed. The result, a burst that appears to chirp downward as its components get stretched out by the turbulent plasma fog. The most fascinating aspect is how these sub-bursts sometimes maintain near-perfect mathematical spacing in both time and frequency, a pattern that hints at clockwork precision beneath the apparent chaos. Some researchers compare it to a stellar resonator, where the magnetar's crust vibrating at specific harmonics generates a cascade of emission layers, each tuned to a slightly lower frequency. Others see parallels with pulsar microstructures, the incredibly fine scale patterns seen in some neutron star radio emissions, suggesting FRBs might be pulsars pushed to their most extreme behavioral limits. What makes 121102's drifting bursts particularly valuable is their consistency. Unlike more erratic repeaters, this source's sub-bursts often maintain similar drift rates across multiple active periods, as if whatever process generates them follows strict physical rules. That regularity could be the key to distinguishing between competing theories. Plasma lensing would likely produce more variable drift patterns as the intervening clouds shift over time, while a magnetospheric origin might show steadier behavior tied to the neutron star's rotation or vibration periods. The implications ripple beyond just understanding FRBs. If frequency drifts indeed trace back to magnetospheric processes, they could give us an unprecedented window into neutron star interiors, regions where matter is compressed into states so dense a sugar cube's worth would outweigh Mount Everest. Alternatively, if plasma lensing dominates, these drifting bursts become probes of the otherwise invisible maelstrom surrounding compact objects, mapping turbulence on scales from millions of kilometers down to meters. Every new downward drifting burst adds another day to point to this cosmic mystery. Are we hearing the staggered cries of a magnetar's magnetic field rebuilding itself after a catastrophic rupture? Or are these signals being reshaped by the most violent particle storms in the universe, their frequencies scrambled like radio stations fading in and out on a long desert highway? For now, each drifting subburst is both an answer and a question, a fleeting clue that brings us one step closer to deciphering the physics of the impossible. One of the most audacious proposals in modern cosmology is using fast radio bursts as intergalactic yardsticks to measure the universe's expansion, a potential game changer in the decades-long debate over the Hubble constant. This fundamental number describes how fast the cosmos is stretching, with profound implications for everything from dark energy to the universe's ultimate fate. Yet there's a problem. Current measurement methods disagree. Observations of nearby galaxies using Cepheid stars and supernova yield one value, while studies of the cosmic microwave background radiation suggest another. The discrepancy, dubbed the Hubble tension, has left physicists scrambling for independent ways to resolve it. Enter FRBs, whose unique properties might just break the deadlock. The method hinges on a simple but powerful principle: dispersion. When an FRB traverses the cosmos, its radio waves interact with free electrons in intergalactic space, slowing down slightly in a predictable way. By measuring this dispersion delay along with the burst's redshift from its host galaxy, astronomers can essentially count the electrons along its path and calculate how much the universe has expanded since the burst began its journey. Unlike traditional methods that rely on complex cosmic distance ladders, FRBs provide a direct route to the Hubble constant. Each burst is like a time-stamped message from across the ages, carrying within it the imprint of every electron cloud it passed through during its billion-year voyage. Early results are tantalizing. A 2020 study using just 14 localized FRBs produced a Hubble constant estimate that intriguingly split the difference between the Cepheid and SIMBI values. While the uncertainties were too large to declare victory, the technique showed promise, especially as more bursts are mapped to their host galaxies. The real power lies in FRB cosmology's ability to bypass the messy calibrations plaguing other methods. Cepheid variables require painstaking cross-checks with parallax measurements, while CMB analyzers depend on intricate models of the early universe. FRB, by contrast, offer a clean, physics-driven approach: count the electrons, measure the redshift, and let relativity do the rest. But the road to precision cosmology is littered with challenges. The biggest hurdle, accounting for the missing electrons, the fraction of free electrons hiding in galaxies or galaxy clusters rather than the diffuse intergalactic medium. These dense pockets can skew dispersion measures like toll booths on a highway, introducing errors if not properly modeled. Some teams are tackling this by focusing on FRBs from galaxies with minimal star formation, where electron contamination is lower. Others are developing sophisticated simulations to subtract local effects, effectively peeling back the layers of cosmic fog to isolate the pristine intergalactic signal. There's also the matter of redshift accuracy. While some FRB host galaxies have well-measured redshifts, others, particularly those in faint dwarf galaxies, require intensive follow-up observations. Future surveys like those planned with the Square Kilometre Array aim to detect and localize thousands of FRBs, building a statistical sample robust enough to overcome these uncertainties. The dream scenario, a golden burst that occurs behind a massive galaxy cluster, whose gravitational lensing effect would split the FRB into multiple images arriving at slightly different times. By comparing these lensed signals, astronomers could precisely reconstruct the burst's path through the cosmic web, providing an exquisitely detailed map of electron distribution along the way. The stakes couldn't be higher. If FRB cosmology confirms one side of the Hubble tension, it might force us to reconsider fundamental aspects of particle physics or dark energy. Alternatively, it could reveal systematic errors in existing methods, reshaping how we measure cosmic distances altogether. What makes FRBs uniquely compelling is their potential to serve as neutral arbiters, a third party untethered from the assumptions underlying current debates. They're not beholden to stellar physics like Cepheids, nor tied to primordial conditions like the CMB. They simply exist as raw, unfiltered probes of the universe's expansion, carrying within their fleeting radio whispers a possible key to one of cosmology's greatest puzzles. Every new localized burst adds another data point to this grand experiment. With upcoming observatories poised to detect FRBs by the thousands, we may soon have enough statistical firepower to determine whether the Hubble tension is real, or if we've been overlooking something fundamental about how the universe stitches itself together across time and space. These enigmatic signals, once dismissed as cosmic oddities, could ultimately become our most reliable guides to the fate of everything. At first glance, some fast radio bursts seem to defy the universe's ultimate speed limit. Their components appear to race across space faster than light itself. Take FRB 120116, where certain features in its signal arrived at Earth with time gaps that, if taken at face value, suggested motion millions of times beyond light speed. But before declaring Einstein's relativity broken, there's a catch. This superluminal effect isn't real. It's a cosmic magic trick, one where turbulent plasma and relativistic physics conspire to create illusions that vanish under closer scrutiny. The illusion unfolds in the chaotic environment surrounding FRB sources. Imagine a Magnetars eruption launching twin shockwaves into its surrounding plasma, one moving directly toward Earth, the other at a slight angle. As these shocks plow through magnetized gas, they generate radio waves at different frequencies. Now picture the angled shock's path being bent by dense plasma, forcing its lower frequency emissions to take a detour before finally heading our way. The result, higher frequency waves from the direct shock arrive first, while the delayed lower frequencies seem to trace a path across the sky, impossibly fast when reconstructed by telescopes. It's like watching a fireworks display through frosted glass. The apparent motion you see isn't the actual movement of objects, but distortions created by the medium itself. This phenomenon, called plasma lensing, has precedent in astrophysics. Pulsars often exhibit similar frequency-dependent delays, their signals scrambled by interstellar electrons. What makes FRBs unique is the extreme scales involved. A magnetar's surroundings can be so densely magnetized that plasma acts like a funhouse mirror, stretching and compressing radio waves in ways that mimic velocities no object could physically achieve. The key clue lies in the signal's polarization. True superluminal motion would warp the radio wave's orientation in specific ways that simply don't match observations. Instead, the burst's preserved polarization fingerprints point squarely to plasma distortion as the culprit. General relativity isn't just safe, it's the very framework that explains the illusion. Einstein's equations allow apparent faster-than-light effects when signals traverse warped spacetime or turbulent media. The classic example is a quasar's jet angled toward Earth, where relativistic beaming creates the illusion of superluminal motion without violating physical laws. FRBs operate on a similar principle. Their emission isn't actually moving faster than light, but the interplay of scattering and path length differences tricks our instruments into seeing phantom speed. The implications stretch beyond academic curiosity. If misinterpreted, these apparent superluminal signals could lead astronomers to false conclusions about FRB engines, perhaps suggesting exotic physics where none exists. Correctly decoding the illusion, however, turns each burst into a probe of the extreme plasma conditions near neutron stars, By analyzing how different frequencies lag or lead, researchers can reconstruct the density and magnetic fields of these invisible barriers with unprecedented precision. Future telescopes may finally settle the debate. Instruments like the next-generation VLA could resolve FRB sources in real time across multiple frequencies, watching as plasma lenses focus and distort the signal like cosmic prisms. Until then, these phantom velocities stand as a reminder. In a universe where space-time bends and matter twists into strange forms, not everything that seems impossible actually is. The truth often hides in the subtle interplay of radiation and plasma, a dance where nature's sleight of hand outshines even its most dazzling explosions. Dark matter, the universe's most elusive substance, makes up 85% of all matter, yet refuses to interact with light, leaving astronomers to track its presence through gravitational whispers. But what if fast radio bursts, those brilliant cosmic flashes, are actually dark matter's hidden language? It's a radical idea that turns conventional astrophysics on its head, suggesting these bursts might not come from neutron stars or collisions, but from the annihilation of invisible particles or the death throes of primordial black holes. Consider this wild scenario. Certain dark matter models predict the existence of action stars, hypothetical clumps of ultra-light particles bound together by quantum forces. If one of these invisible orbs were to collapse under its own gravity, the resulting burst of decaying actions could convert into radio waves in the presence of strong magnetic fields, producing an FRB's telltale millisecond spike. The math almost works, the energy scales align, and the lack of afterglows fits dark matter's ghostly nature. Even more intriguing, this could explain why some bursts seem to originate in empty intergalactic voids, where visible matter is scarce but dark matter should be abundant. Then there's the primordial black hole angle, the idea that the early universe birthed countless tiny black holes, some no heavier than a mountain yet as small as an atom. If these ancient relics still drift through space today, their final moments evaporating via Hawking radiation could unleash energy tantamount to a nuclear blast compressed into radio frequencies. The kicker, these micro-black holes would vanish without a trace post-burst, leaving no neutron star or debris behind, just the kind of one-and-done FRBs we observe. Mainstream cosmology, of course, raises skeptical eyebrows. For dark matter annihilation to produce FRBs, the particles involved would need coupling strengths to electromagnetic fields far beyond current limits, a stretch even for theorists comfortable with the unknown. And primordial black holes remain hypothetical, with observational constraints suggesting they can't account for all dark matter, let alone frequent cosmic radio bursts. Critics also point to FRBs localization in star-forming galaxies as evidence against dark matter origins. If bursts were tied to invisible mass, why would they cluster where regular matter thrives? Yet the allure of this fringe theory lies in its ability to explain FRB outliers, the bursts that refuse to fit neutron star paradigms. Take FRB 150215, the dark burst with no multi-wavelength counterpart. If dark matter is truly invisible, wouldn't its explosions lack the X-ray or optical afterglows we associate with baryonic physics? And why do some repeating FRBs show energy outputs that strain magnetar models, yet align neatly with theoretical dark matter particle masses? The debate embodies science at its most thrilling, a tug-of-war between Occam's razor and the tantalizing possibility of paradigm shifts. Until we detect dark matter directly or rule out primordial black holes conclusively, these hypotheses will linger at the edge of plausibility, reminding us that the universe's greatest mysteries often hide in plain sight. Whether FRBs are dark matter's dying screams or just magnetars showing off, one thing's certain: their secrets are forcing us to question everything we think we know about the invisible scaffolding of reality. Some fast radio bursts arrive not as clean signals but as cosmic echoes, their radio waves bouncing off unseen obstacles before finally reaching Earth, creating ghostly repeating patterns. FRB 170107 stands out as the prime example, its initial millisecond spike followed by a sequence of fainter copies spaced almost perfectly 1.7 milliseconds apart. These delayed replicas aren't random noise, they're a celestial echolocation experiment, revealing hidden structures between galaxies that no telescope could ever see directly. The leading explanation for these echoes is interstellar scattering, the idea that dense plasma clouds act like cosmic mirrors, reflecting portions of the burst's energy along slightly longer paths. Picture shouting into a canyon and hearing your voice rebound off distant cliffs. The time delay between your call and its echo reveals the canyon's size. Similarly, the 1.7 millisecond gap in FRB 170107's echoes suggests the signal grazed a plasma structure roughly 250 astronomical units across. That's 5 times larger than Pluto's orbit. The kicker, this reflective barrier lies somewhere along the burst's billion light-year journey, possibly near its host galaxy or even within our own Milky Way. But there's a twist that complicates this tidy explanation. Some echoes show frequency-dependent delays. Their lower radio frequencies arrive later than higher ones, a fingerprint of dispersion that shouldn't occur if simple reflection were at play. This has led astronomers to consider even wilder scenarios like gravitational lensing from invisible dark matter clumps. According to general relativity, massive objects warp spacetime, bending passing radio waves like a glass lens bends light. If an FRB's path grazes a cluster of rogue black holes or a knot of dark matter, its signal could split into multiple images, each taking a slightly different route to Earth. The result, an echo pattern that carries encrypted details about the lens's mass and shape. Then there's the magnetospheric echo hypothesis, the idea that these repeating patterns originate not from external obstacles, but from within the FRB engine itself. Imagine a magnetar's crust fracturing like a frozen lake, sending seismic waves rippling across its surface. Each new crack could launch another radio pulse milliseconds after the first, creating an echo effect without any interstellar mediation. Supporting this, some repeating FRBs show echo-like sub-bursts that vary in polarization, suggesting their delayed components emerge from different magnetic environments on the neutron star's surface. The most tantalizing echoes defy all these models entirely. FRB 121102 occasionally produces mirror image bursts, near-perfect replicas of earlier signals, but with inverted polarization, as if the waves ricocheted off a magnetic mirror that flipped their orientation. No known natural phenomenon easily explains this behavior, leading some theorists to speculate about exotic plasma physics or even coherent reflection from hypothetical quantum objects like action stars. What makes these cosmic echoes more than just curiosities is their potential as universe mapping tools. By carefully timing echo delays, astronomers could reconstruct the 3D distribution of plasma clouds across intergalactic space, the invisible scaffolding upon which galaxies are built. Future observations might even catch an FRB echoing off a passing star or black hole's accretion disk, offering a fleeting chance to study these objects without directly observing them. Every echo is a whisper from the dark, a clue that the universe's emptiest spaces are far more textured and far stranger than we ever imagined. Fast radio bursts don't just vary in brightness or repetition. They come packaged in radically different spectral shapes, some razor-thin in frequency while others sprawl across the radio dial like cosmic static. Take FRB 180916's elegant narrowband emission, concentrated in a sleek 200 MHz slice, versus FRB 190611's chaotic broadband blast roaring from 400 MHz to 8 GHz. This staggering diversity isn't random noise. It's a cipher holding secrets about the engines powering these bursts and the brutal environments they erupt from. Narrowband bursts like FRB 180916s suggest an emission process fine-tuned to specific frequencies, almost like a cosmic laser. One compelling theory points to plasma resonance effects in magnetospheres, regions where charged particles oscillate in sync with magnetic fields, amplifying certain radio wavelengths while suppressing others. Picture blowing across a soda bottle's rim to produce a pure tone. The Magnetars magnetosphere might act similarly, with its size and magnetic field strength dictating the note we receive. This could explain why some bursts appear bandwidth limited, their energy funneled into a tight frequency band by the precise physics of their birthplace. Broadband monsters like FRB 190611 tell a different story, one of unbridled chaos. Their sprawling spectra resemble the crackle of lightning or the hiss of a detonating star, signatures of shockwaves plowing through turbulent plasma at relativistic speeds. These bursts likely originate in environments where magnetic fields are so twisted and dynamic. They accelerate particles across an extreme range of energies, generating radio waves at virtually all frequencies simultaneously. The result, a signal that doesn't just pierce the static but drowns it out entirely, a broadband roar echoing across the cosmos. The real puzzle lies in the outliers, bursts that switch spectral personalities mid-eruption. FRB 121102, the first known repeater, has produced both chirping narrowband subbursts and sweeping broadband emissions during different active periods. This Jekyll and Hyde behavior hints that multiple emission mechanisms might coexist in the same object, with one dominating under certain conditions. Perhaps a magnetar's crust fracture starts with a focused plasma resonance narrowband before triggering messy magnetic reconnection broadband, like a precision surgical tool giving way to a sledgehammer. Astronomers are now racing to decode what these spectral shapes reveal about the universe's hidden physics. Narrowband bursts could be mapping the resonant frequencies of neutron star magnetospheres, offering a way to weigh these dense objects remotely by their spectral fingerprints. Meanwhile, broadband bursts serve as probes of intergalactic turbulence, their high-frequency components getting scraped away by electron clouds over billions of light-years, leaving only the hardiest low frequencies to reach Earth. The most tantalizing possibility, that bandwidth itself could distinguish FRB origins. Some models suggest compact mergers like colliding neutron stars should produce broadband bursts from their messy debris clouds, while orderly magnetar flares might lean narrowband. If confirmed, this spectral divide would let astronomers classify bursts at a glance, separating cosmic catastrophes from stellar temper tantrums by the width of their radio screams. As telescopes grow more sensitive, the spectral zoo keeps expanding. Recent detections include bursts with Notch's mysterious frequency gaps where the signal abruptly vanishes, possibly due to absorption by helium clouds near the source. Others show bandwidth wobble, their frequency range oscillating in sync with a magnetar's spin. Each new shape is a piece of the puzzle, revealing that FRBs aren't just one kind of cosmic explosion, but a spectrum of violence written in radio light. The challenge now is learning to read their spectral signatures like a forensic scientist reads fingerprints, extracting the story of each burst's birth, journey, and the unseen forces that shaped its cry across the void. Imagine a cosmic radio station that occasionally goes silent for months or even years without warning. That's the eerie pattern astronomers face with fast radio bursts, where detection rates mysteriously plummet during what scientists call FRB droughts. These puzzling lulls raise fundamental questions. Are we missing bursts because our telescopes aren't listening at the right moments? Or do the sources themselves switch off for extended periods like celestial hibernators? The challenge begins with the uneven nature of FRB observations. Unlike steady cosmic phenomena such as pulsars, which tick with predictable regularity, FRB detection depends on unpredictable eruptions and on telescopes happening to point in the right direction at the exact millisecond they occur. Even high-sensitivity instruments like CHIME, which scans the entire northern sky daily, sometimes log weeks with few or no bursts, followed by sudden flurries of activity. This inconsistency isn't necessarily evidence of dormant sources. It could simply reflect the statistical randomness of rare events. Throw in the seasonal downtime for telescope maintenance, weather interference, or radio frequency pollution from Earth-based sources, and distinguishing true cosmic silence from observational gaps becomes a nightmare. Yet some droughts defy simple explanations. In 2020, astronomers noticed a chilling trend. Several previously hyperactive repeaters, including the famous FRB 121102, abruptly stopped transmitting for over a year. This wasn't just bad luck in telescope coverage. Dedicated monitoring campaigns confirmed the sources themselves had gone quiet. The leading theory, Magnetars, the prime suspects behind many FRBs, might enter extended, calm periods when their crusts stabilize after violent quakes, temporarily pausing the magnetic turmoil needed to power burst. Even stranger are the global droughts periods when all FRB detection rates drop worldwide, regardless of telescope or sky coverage. One such lull in 2019 saw a 60% reduction in burst discoveries across observatories from Australia to Canada. Some speculate these could trace back to large-scale cosmic, whether intergalactic plasma storms or shifts in the solar wind, creating temporary radio static that masks distant bursts. Others suggest a more unsettling possibility, that FRBs aren't randomly distributed in time but follow clustering patterns we don't yet understand, like seismic aftershocks or solar flare cycles. The solution might lie in emerging FRB weather forecasts, statistical models predicting active and quiet periods based on historical data. Preliminary work hints at rough 2-year cycles for some repeaters, possibly tied to magnetar precession or orbital dynamics in binary systems. Meanwhile, next-gen telescopes like the Deep Synoptic Array in California are minimizing observational gaps with near-continuous coverage, separating true cosmic silence from earthly limitations. What makes these droughts more than just technical nuisances is what they reveal about FRB engines. If sources can switch off for years, it suggests their power isn't inexhaustible. Whatever reservoir fuels these bursts eventually depletes, then mysteriously refills. Whether it's magnetic energy rebuilding after a starquake or debris slowly accumulating around a black hole, these silent intervals could be the key to understanding the recharge cycle of the universe's most enigmatic radio transmitters. Until the next burst breaks the hush, astronomers keep listening, knowing that sometimes the universe's loudest messages hide in its quietest moments. Beneath the extreme physics of fast radio bursts lies a deeper mystery, one that might not just bend the rules of astrophysics, but rewrite the textbooks on quantum mechanics itself. Picture a neutron star's core, a swirling ocean of neutrons so densely packed they cease behaving like ordinary matter and instead flow as a frictionless superfluid. Under these conditions, quantum effects typically confined to microscopic scales suddenly dominate an object the size of Manhattan, potentially unlocking bizarre new ways to generate cosmic radio explosions. Superfluidity inside neutron stars isn't just theoretical pulsar glitches, where these stars suddenly spin faster, are thought to be caused by vortices in the superfluid core suddenly unlocking from the crust. But what if FRBs represent an even more violent superfluid upheaval? Some models suggest that quantum tornadoes within the superfluid could generate colossal magnetic bubbles, which, when they burst through the star's surface, might channel energy into focused radio beams. The math reveals something astonishing. These quantum fluid dynamics could convert neutron star spin energy into FRB-like bursts with near-perfect efficiency, sidestepping the power limitations of traditional magnetar flare models. Then there's the wild card of cosmic superconductors. Neutron star interiors may host protons pairing up in Cooper pairs, the same quantum phenomenon that enables earthly superconductors to carry current without resistance. In the extreme pressures of a magnetar's core, these paired protons could form macroscopic quantum states capable of storing immense magnetic energy. If such a superconducting region suddenly collapsed, perhaps due to a starquake, the released energy might not just produce an FRB, but do so with the spectral purity seen in some narrowband bursts, like a cosmic violin string vibrating at a single perfect pitch. The quantum weirdness escalates when considering vacuum breakdowns. Near a magnetar's surface, magnetic fields can become so strong they distort the very fabric of quantum vacuum, creating pairs of particles from empty space. Simulations show these conditions might trigger an avalanche effect, a chain reaction where vacuum decay ripples outward, releasing energy in a radio frequency shockwave. While speculative, this mechanism elegantly explains why some FRBs show such remarkably clean signals, as if the burst emerged from a quantum process unfiltered by chaotic plasma. Of course, linking FRBs to quantum physics isn't without controversy. Critics argue these ideas often rely on untestable extrapolations of quantum theory to regimes trillions of times more extreme than any lab experiment. Yet the mere possibility forces us to confront how little we know about matter under such conditions. Every FRB could be a laboratory for physics beyond our reach, a natural quantum experiment playing out in the cosmos, whispering hints about how the universe behaves when the rules themselves begin to fray. What makes these quantum connections tantalizing isn't just their explanatory power, but their testability. If superfluidity plays a role, we might detect correlated FRBs and pulsar glitches from the same neutron star. Superconducting collapse models predict specific frequency drifts in repeating bursts as the progenitor's core recovers. Even vacuum breakdown scenarios leave potential imprints, unique polarization signatures that next-gen telescopes could identify. The universe has a habit of being stranger than we imagine, and FRBs may be the key that finally unlocks the quantum secrets hiding in plain sight, written across the sky in bursts of radio light. The future of fast radio burst science hinges on a new generation of telescopes, machines so powerful, they'll transform these cosmic enigmas from mysterious anomalies into precision tools for probing the universe. Leading this revolution is Canada's CHIME telescope, a sprawling array of half-cylinder reflectors resembling snowboarding halfpipes, scanning the entire northern sky every day with unprecedented speed. Already, CHIME has rewritten the playbook by detecting thousands of FRBs since its 2017 debut, including rare repeating bursts that earlier instruments might have missed. But the real game changer looms on the horizon: the Square Kilometre Array, or SKA, an international megaproject spanning continents with thousands of radio dishes and antennas. Once completed in the late 2030s, SKA won't just detect FRBs, it'll dissect them with surgical precision, capturing their polarization, dispersion, and scattering in real time across frequencies from 50 MHz to 20 GHz. What makes these next-gen instruments revolutionary isn't just sensitivity, it's their ability to localize bursts instantaneously. Current telescopes often require weeks of follow-up to pinpoint an FRB's host galaxy, but SKA's vast intercontinental baseline will triangulate positions within seconds. Imagine catching a burst and immediately knowing which galaxy it came from, then swiveling optical telescopes to witness the aftermath, a coordinated multi-messenger assault on the mystery. Even more groundbreaking is SKA's planned ability to monitor thousands of square degrees simultaneously, effectively creating a real-time FRB early warning system that could catch the elusive moment when a magnetar's crust fractures or neutron stars collide. The physics breakthroughs these telescopes promise are staggering. With enough precisely localized bursts, astronomers could map the cosmic web's hidden matter in 3D, using dispersion measures like sonar pings to reveal filaments of warm gas stretching between galaxies. Polarization data from SK might finally distinguish between competing FRB theories. If bursts from spiral galaxies show systematic polarization differences from those in dwarfs, it could confirm environment-dependent formation mechanisms. There's even speculation about detecting Faraday rotation anomalies, subtle twists in polarized signals that could betray the presence of hypothetical action like dark matter particles along the burst's path. Beyond brute force detection, machine learning is set to transform how we study FRBs. New algorithms can now sift through radio interference to find faint bursts older instruments dismissed as noise, while neural networks trained on simulated magnetar flares are uncovering subtle patterns in repeater sequences that hint at underlying periodicity. Some systems already predict when certain repeaters might activate based on magnetic field models, turning FRB hunting from a passive waiting game into an active search guided by artificial intelligence. Perhaps most tantalizing is the potential for entirely new classes of FRB-related phenomena. Just as the first radio telescopes revealed pulsars and quasars, SK-class instruments might discover millisecond-long counterparts to gamma-ray bursts, or perhaps dark FRBs, signals so heavily scattered by intergalactic plasma that they smear into undetectability at lower frequencies. There's even hope of catching an FRB in the act of lensing around a foreground galaxy, an event that would let astronomers weigh dark matter halos with precision while testing general relativity across cosmic distances. The coming decade promises more than just answers, it guarantees surprises. Every time humanity has built telescopes with tenfold better sensitivity, we've uncovered phenomena nobody predicted. From pulsars to dark energy, history shows that when we expand our senses, the universe reveals layers of complexity we never imagined. Fast radio bursts, once curiosities at the edge of detectability, are about to step into the spotlight, not just as mysteries to solve, but as tools to rewrite our understanding of everything from quantum physics to cosmology. The cosmos has been flashing its radio lighthouse at us for billions of years. Now, at last, we're building telescopes that can truly read the signal. From their mind-bending energy outputs to their unpredictable repeating patterns, fast radio bursts have shattered every assumption we had about cosmic radio signals. Think about it, we've uncovered bursts that outshine galaxies in milliseconds, signals that echo like cosmic sonar, and repeating patterns that defy all known physics. Some arrive with clockwork precision, while others vanish without a trace. Some are tied to magnetars in our own galaxy, while others scream across billions of light years from mysterious dwarf galaxies or serene spirals. And let's not forget the strangest of all, those whispering hints of quantum superfluids, dark matter, or even space-time itself unraveling. What makes FRBs so revolutionary isn't just what they are, it's what they represent. These bursts are forcing us to rewrite the rules. They've exposed gaps in our understanding of magnetic fields, particle acceleration, and even the distribution of invisible matter woven between galaxies. Every time we think we've pinned them down, a new detection comes along, a low dispersion anomaly, a microsecond flash, or a burst that shouldn't have an afterglow but does, and suddenly the puzzle gets more complicated. But here's the beautiful part, we're just getting started. With telescopes like the Square Kilometre Array coming online, we're on the verge of catching FRBs in real time, dissecting their polarization, and maybe, just maybe, watching one ignite in tandem with gravitational waves or a gamma-ray burst. The next big discovery could be lurking in the data we've already collected or hiding in the static of tomorrow's observations. So stay curious, because somewhere out there, in the vast dark between the stars, another burst is brewing, a signal that could upend everything we think we know. And when it arrives, it won't just be another mystery. It'll be an invitation to look deeper, question harder, and remember that the universe always has one more surprise up its sleeve. The story of FRBs isn't just about radio waves. It's about our endless quest to understand the cosmos, 1 millisecond flash at a time. And trust me, the best chapters are still